Okay, so let's look at the following example. Make this a little bit bigger. For what values of the parameter t are the columns of A linearly independent? Now, technically, okay, so let's start out simple. So if we were to use the definition, so let's write a solution. I could skip this part, but I just want you to understand what we're doing, okay? What does that mean that we want the columns to be linearly independent? That means that if we take scalars, say lambda 1 times the first column, plus lambda 2 times the second column, plus lambda 3 times the third column, and compare that to 0, then there should only be the trivial solution. In other words, we need to prove that lambda 1, lambda 2, lambda 3 are 0. So we need to are necessarily 0. The thing is, this is kind of redundant, right? So we have to show that lambda 1 equals to lambda 2 equals to lambda 3 equals to 0 is the only solution. Okay? Or for what t's? So let's see, we're asking when they're dependent. Okay, so let's first of all clarify. What I just wrote is linear independence. Okay, so this is the definition of linear independence. That there's only one solution to this equation, which is trivial. So that means that linear dependent means that we'll be able to find a non-trivial solution. In other words, a solution that at least one of these lambdas is non-zero. And in practice, that pretty much means, if we're working over the real numbers, that we'll just have an infinite number of solutions to the corresponding homogeneous equation. Now, if you rewrite this in matrix form, you're pretty much going to get this with zeros over here. So let's look at that. So in a sense, we could have just skipped all of this. So our goal is to find for what values of t we have an infinite number of solutions. So I'm writing this as a matrix, and I'm going to use Gaussian elimination. And I'm not going to reach canonical form. Okay. So first of all, this -2 is annoying, and I could divide by -2, but what I'd rather do is just swap between the first and second row. So let's swap between R1 and R2. That's the first thing we'll do. So that means, first of all, I want to duplicate this. And that means we're swapping between R1 and R2. I'm also swapping the zeros, but if we swap the zeros, we get the same thing. Some people don't bother to write the zeros over here. I like to write them, but you don't really have to write them if you're aware that, that they're technically over on the right-hand side. So we have a 1 in the upper left-hand corner of the new matrix. And now our goal is to remove these two zeros. Okay? So how can we go about that? Well, we can copy this arrow. And then ask ourselves, how could we get rid of this -2? Well, we could do R2 becomes R2 plus 2 times R1, right? So this 1 times 2 plus -2 is 0. And we could ask, how could we get rid of 1 in row number 3? So that's actually simpler. It's just R3 becomes R3 minus R1. Okay, great. So first of all, we have not changed the first row, so I can copy that. And I selected the elementary operations so that there will be zeros here. Now this part's definitely going to be 0. It's kind of redundant even to write this, but I like to write it. And now what about this part right here? So it's going to be R2, in other words, the number 1, plus 2 times t. So 1 plus 2t. That's, let's make just a little bit more space. So 1 plus 2t is over here. What about over here? So it's R2, that's negative 2, plus 2 times 0. Well, 2 times 0 is 0. Next, let's move down to here. So that means we want to take R3. R3 is 0 minus R1. That's 0 minus t. In other words, negative t. Finally, we have negative t in R3 minus R1, which is 0. So that's our new matrix. Let's actually move all of this down here. And first of all, okay, this is getting a little bit tricky now. So notice that if t equals to 0, we'll have an infinite number of solutions. So if t equals to 0, then let's actually write this out instead of looking at my handwriting. So if t equals to 0, then there exists non-trivial solutions. So the columns of A are linearly dependent in this case. So let's assume that t is not equal to 0. And what's the great thing about numbers that are not equal to 0? We can divide them, right, without any fear. So what we'll do is take this result under the assumption that t is not equal to 0. And let's change the third row. So let's do R3 becomes negative 1 over 2 times R3. I'm getting rid of these t's over here. So I haven't changed the first two rows. So that gives us a 0, a 1, and a 1, and a 0. And next, I prefer to swap the second and third row. So let's swap them. So I'm going to do, let's swap between R2 and R3. So I haven't changed row number 1. And now what was the third row will be the second, and which was the row which was previously the second will now become the third. And we have the zeros over here still. And now let's use this 2 to get rid of this 1 plus 2t. So I'll do R3, right? We're trying to change row number 3, becomes R3 minus something times 1, which will cancel this. Well, that only can be 1 plus 2t times R2. Came out a bit big, so let's shrink this. And notice that we've only changed row number 3. So I can just duplicate row 1 and row 2. Now we chose the elementary row operations so that this becomes 0. And now we just have to figure out this part. Right, this will be 0 too. So this part over here is going to be negative 2 minus 1 plus 2t times R2. R2 is 1. So we just have to be careful now, simplifying. It's negative 2 minus 1 minus 2t. So that's minus 3 minus 2t. So let's just write that over here. excuse me, I'll undo that in case you're looking at this. So minus 3 minus 2t. And now the only way to have a non-trivial solution is if this is 0. So there is a non-trivial solution if negative 3 minus 2t is equal to 0. And that is, or in other words, if t equals to, I think it's negative 3 over 2. Yeah. And non-trivial solution means linearly dependent. So let's summarize. So the columns of A are linearly dependent if and only if t is either equal to 0 or negative 3 over 2. T equals to 0 or t equals to negative 3 over 2. And it's or, it's not and. And is absolutely wrong because there does not exist any number in the world that can be simultaneously 0 and negative 3 over 2. That's it. Now there's another solution using determinants, which I won't present now. Okay, so have an amazing day and happy matrices, I guess. Happy linear algebra.